And let's come back to our slide. So yes, the midterm will be proposed. I've already posted a message on the blackboard. But I will let you know it will at least postpone by a week at least. Okay. So it will not be on March 4. I'll say again, the range of the midterm will be to momentum, to the chapter of momentum. Okay. Now this is a work energy theorem. Okay, we've just derived. F, the work done by the force, is equal to the change in kinetic energy, right? That is a work energy theorem. Suppose now the force, now up to this point, we haven't imposed any condition on the force F. The force F could be arbitrary. It is not necessary that the force is a conservative one. Okay. We have assumed a very general force up to this point. Okay. But now we insert a condition. We impose the condition of a conservative force. We now assume that the force F is conservative. And if the body is acted by only one conservative force, which is F, then the integral of F dx with a minus sign will what? Will be equal to what? As according to our previous discussion, this integral will be equal to the difference in potential energy between the 2 points. And that is ux2, the u at the final position, minus ux1, the u at the initial position. And that is the potential energy difference between the 2 points, between the final and initial position. So I denote that by delta u. But you see the same integral, the same work done is equal to the change in kinetic energy, right? That is the first condition. That is the work energy theorem for the kinetic energy we found, right? And by the definition of the potential energy, we got the same integral, but with the minus sign equal to the change in potential energy between the 2 points. And so what does that mean? That means the change in kinetic energy and the change in potential energy are equal in magnitude, but of the opposite sign. Delta K is equal to minus delta U, or delta K plus delta U is equal to 0. What does that mean? That means the total change in kinetic energy plus the total change in potential energy is 0. Okay, so if one quantity increased, the other quantity will decrease. If the delta K is positive, delta U is negative. If delta U is negative, delta K is positive. The change always remains in opposite sign, and they have the same magnitude. So they add up to 0. And what does that mean? That means the total energy, the total potential and kinetic energy, when the two energy added together, that remains a constant. If I take out the delta, that means delta K plus U is 0. And delta is a change. So that means a change in K plus U always remains 0. And there's just no change in the sum of K and plus U. And so the total mechanical energy of the system, which is the K plus U, is equal to a constant. And that means total energy is conserved. The mechanical energy, which consists of the sum of potential energy and kinetic energy, is conserved. Okay. Now, so what it means here is the following. If the system is acted only by one force, and that force is conservative, for example, gravity, then the work done by that conservative force will only allows the kinetic energy and the potential energy to exchange each other. Sometimes The kinetic energy becomes the potential energy, and the potential energy sometimes becomes the kinetic energy. But the sum of the potential and the kinetic energy always remain constant. It's always conserved. The total mechanical change is conserved. It does not change. And that is the conservation of mechanical energy. When a system is acted only by one conservative force, then the work done by the conservative force only allows U and K, the kinetic and potential energy, to exchange each other. But the total mechanical energy remain constant. And that constant I call it total energy E. Okay. Kepler's law is an example of. Kepler's law is not only an example of conservation of energy, it's an example of conservation of mechanical energy and also conservation of angular momentum. You still need another conservation law to get Kepler's law of motion. Okay. Later we'll discuss it when we come to the chapter of gravity. Now, so if you start with the initial position x1, initial velocity v1, and you go to another point, which is x2, with final velocity v2, you find that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. This is the expression you learn in high school. Okay, the kinetic energy plus the potential energy become a constant, and that is the total energy. When you throw a body vertically up into the sky, the potential energy increase, right? But the kinetic energy decrease. So the ball slowly decrease in speed when it ascends, right? And when it goes to the highest position, it falls down. So when you go up, potential energy increase, kinetic energy decrease. And when it goes down, it accelerates by gravity. And so the potential energy becomes kinetic energy again. But the total energy remains constant. Okay. Now, so if U is mgx, x is two level, x1 and x2, then you substitute U here to be mgx at the two different positions. You get the equation you learned in high school. That is the conservation of mechanical energy near the surface of the Earth. And the conservative force is gravity. Okay. Now, how about a spring mass system? If you put U to have an expression of half k squared, you get the kinetic energy plus the potential energy of a spring being equal constant. Okay. So that is a spring mass system conservation. Okay. And how about if I have an object that is placed at a large distance from the Earth? So the potential energy is no longer given by mgh. It is given by minus gmm over r. And with this potential energy, we define the infinity as a reference position. And so if my apple is now at the distance r1 and r2 from the Earth center, and the potential energy will be minus gmm of r1 and minus gmm of r2. So if my apple fall from here to here, the initial kinetic energy will be maybe half mv1 squared. The potential energy is half minus gmm of r1. When it goes to this position, the new position, the potential energy is minus gmm of r2. The kinetic energy is half mv2 squared. So you can now use this relation to solve a energy conservation problem, even when the apple is very far away from the Earth. You just replace the potential energy expression, mgh, close to the surface of Earth, by the general expression of minus gmm of r. Okay. Now let's have a very simple example. That is a spring mass system. Suppose the spring constant is given by this. And initially, the spring is stretched to an extension of 0.2 meter, 20 cm. And then the block is let to release. The block has a mass 0.8 kilogram. And so I would like to ask, what will then be the speed of the block when it just passes the equilibrium position? So I stretch the spring by pulling the block, and I release the block. So the spring pull me back, right? So it accelerates the block. And I would like to ask, what would it be the speed of the block when you just go back to the initial equilibrium position? Because the spring accelerates the block, so the block has a certain velocity, even when it passes the equilibrium position. And I want to find that velocity. So I apply the conservation of mechanical energy. Initially, I release the block from rest. So the initial speed is 0. The initial potential energy is half k1x1 squared, right? Where x is equal to 0.2, right? 0.2 meter. This is the initial extension. The final extension is 0. So the final potential energy is 0. The final kinetic energy is half mv2 squared. So that is just a conservation of energy. And so I can solve for V2. V2 is square root k over m, x1. And I substitute this number, I get 0.4 meter per second. Okay, so that is a simple example of application of conservation of mechanical energy. Now here is a more complicated example. Suppose an asteroid, asteroid is a small planet, okay? Maybe a meteorite, not an asteroid, because it falls to the Earth. So initially the meteorite is at a distance of 10 r from the center of the Earth, where r is the Earth radius. And it's heading directly towards the Earth. It has an initial velocity of 12 kilometer per second. It's heading towards the Earth. That is the velocity at the distance 10 r from the Earth. And I would like to find the velocity of the asteroid when it hits the surface of the Earth. And when it hits the surface of the Earth, the distance is 1 r from the center of the Earth, right? So I would like to apply the conservation of mechanical energy. But since I'm talking about a large distance from the Earth, I use the general expression for the potential energy, minus gmm over r, okay? R1, the initial position, is 10 times the radius of the Earth, so 10 capital R. The initial velocity, I convert this into SI unit, 1.2 times the power 4 meter per second. Finally, when the asteroid collides with the surface of the Earth, the distance from the Earth center is r, the radius of the Earth. The final velocity is what we want to find. So we substitute all this into the equation. Okay, we will plug in this number at the end. We rearrange this equation so we make V2 the subject of the formula. And so we got this number, and we take a square root. The initial distance is 10 r, the final distance is r. Okay, so we have this factor. And eventually, after moving all the terms to the right and taking the square root, we plug in this number, gravity or constant, the mass of the Earth, the radius of the Earth, and also the initial velocity V1. We got the velocity when the asteroid hits the surface of the Earth. Okay. So that is a quick review, just to quick classwork, just to wake you up. Suppose the body is released from a distance 2 r from the center of the Earth, where r is of course the Earth radius. So find its speed when it collides with the Earth's surface in terms of gm and r. Just a very quick question. You should be able to do it in 2 minutes. Why not try to do it now? Okay. Have you got the answer to this problem? Now let's do it together, okay? The initial velocity is 0 because the object is released from rest, right? So we have this to be 0, right? Initial potential energy is what? Initial distance is 2r from the center of the Earth. So the potential energy is minus GMM over the distance, 2r, right? The final kinetic energy is what we want to find. So we denote the final velocity at V2. And when it hits the Earth's surface, the final potential energy is GMM over r, right? There's a distance from the center of the Earth. So you now with this equal to 0 and the m cancel, right? So you have a V2 square. You move this term to the left. 1 minus 1/2, right? So it's equal to 1/2. And that 1/2 will cancel with this 1/2 on the right hand side. So you now have GM over R. You take the square root of this, you have V2 equal to GM over R square root. And that is the answer. Okay. Any problem for this question? Now, what we have discussed, there's a little bit confusion about the work done and the energy transfer, actually. So we better clarify those concepts by using a simple diagram. Now, what we emphasize in our previous discussion is that when we have an external force, the external force may come from my hand pulling the object, or come from a Superman holding the Apple 5 from the infinity to the present position. When we come from the external force, when the work done comes from external force, it always changes the energy of the system. And in the previous discussion, we have named 2 examples. If you have external force, and external force stretch a spring, for example, then the work done by the external force goes to the change in potential energy. The spring has an increase in elastic potential energy because you stretch the spring, right? Okay. So, so the work done by the external force is always change the energy of the system. And in some cases, it goes to the potential energy. It increases the potential energy of the system. Now, suppose the object is not tied by a spring to the wall. It is freely movable along a smooth table. So if you apply an external force to the object, the energy goes to where? It does not go to the potential energy no more because there's no spring. But it goes to what? It goes to a change in kinetic energy. So the work done by the external force will go to the change in the kinetic energy. It makes the object to move faster. Okay. But in any case, as long as you are talking about external force, it does work on the system. It always changes the energy of the system. If it does positive work, then the system will increase in energy, either in the form of potential energy or in the form of kinetic energy. Okay, this is clear. Now, these 2 equations we already have proof. Okay. Now, but the interesting case that we discuss about mechanical energy, when we discuss about the conservation of mechanical energy, is that we are talking about the internal force. Now, the internal force in this case of the spring mass system is a force that due to the spring on the mass. Okay, that is the internal force. And in this case, the internal force is actually conservative. Okay, And also in the case of a block falling under gravity, we take the block and the Earth as a whole, as a system. And internal force in this case is the force of gravity pulling down the block, pulling the block down, right? So what does the internal force do? Is that the internal force does not change the total energy of the system, but it only allows the interchange of kinetic energy and potential energy of the system. So in this case, for example, if I have compressed the spring and I release it, the spring potential energy will go back, will change back to kinetic energy and will push the block, accelerate the block to high velocity. Okay, so the potential energy and the kinetic energy, they just interchange with each other. And delta K plus delta U is always equal to 0. That is the conservation of mechanical energy. So the total energy now does not change because it's the work done by the internal force, not the external force. But the internal force does work to allow for the interchange between the kinetic and the potential energy. Does it make sense? Now, how about this case? The internal force is the gravity force mg. The gravity force mg does work such that there is an interchange between the kinetic energy and the gravitational potential energy. But the total change of energy of kinetic and gravitational potential energy of kinetic and gravitational potential energy, the two change added together is 0. And that is the conservation of mechanical energy. Okay. Now here is an interesting example. Imagine you now have a bowl. You literally have a bowl. Okay, there's a bowl is like this. You release a marble at the top, at the inner surface of the bowl, and let it slide down. So how would it move? It will be sliding back and forth, right? About the minimum, middle minimum position. So the marble will be going vibrating up and down, right? Like this. And when after it dissipated energy, it will settle at the minimum position of the bowl. Is that right? Now we have such a bowl. Essentially, we have a bowl. But that is not a bowl, it's a potential energy curve. It is a one-dimensional problem, okay? Not two-dimensional. But the potential energy has a minimum position at the point x0. And now I release the object. at the position x2. Okay, so the object is now released at rest. And at the point of release, the total energy is the potential energy. The total energy is the energy E, the mechanical energy of the system, and that's equal to the potential energy as U2, as x2. Well, okay. Because we now release the object at rest, so initially it does not have a kinetic energy. Okay, but we know that the sum of the kinetic energy and the potential energy is conserved. So initially we have all the energy as the potential energy, which is Ux2. Okay. Now the marble now slide down. The force is always pointing to the direction of decreasing U. So it goes to the negative side, right? It goes to the negative x direction. Okay, so it slide down. Okay, so it gets accelerated by the conservative force. But after passing through the minimum position, you can see the conservative force is going in the opposite direction to the velocity. So it decelerates the object until it reaches the other side. The other side is the position x1. At this position, again, the total mechanical energy is equal to the potential energy at x1. This two position has the same potential energy. Okay, so at this two position, the kinetic energy is 0. And that means the position x1 is the turning point. When the object goes to the position x1, it is momentary at rest. And after that, it slides down again and go back to the position x2. So imagine the object is now swinging back and forth between these two positions. It goes to the farthest left-hand side, and that's x1, and that swings back to the farthest right-hand side, and that's x2. It swings back and forth between these two positions. Okay. And at the extremum point, at x1, x2, all the energy is potential energy. The object is instantaneous at rest at these 2 points. And in the middle, the object is get accelerate and then decelerate, get accelerate and then decelerate. It swing back and forth like this. And about the equilibrium position x0. Okay. So that is an oscillation. We haven't discussed about oscillation until the chapter of simple harmonic motion, but there is early discussion about that. Now, but how can we know the velocity of the object at any instant, at any position, should say? Now, that is easy to find. We know that the kinetic energy and the potential energy, they add up to be a constant. And that constant is E, the total mechanical energy. So we now can find the kinetic energy by E minus U, where U is the potential energy at any point along its path. Okay. But the kinetic energy is half mv squared, right? So half mv squared is equal to E minus U. We multiply by 2, divide by m, and take square root, we find the velocity. The velocity is given by square root 2 E minus U over m. Now you can see the velocity of the object is proportional to the square root of E over U. Now E is this horizontal line, the total energy. And U is this curve, right? So E minus U is what? Is a distance between the horizontal line and the potential energy curve. So you can see when E minus U is maximum, the velocity is maximum. Where does it happen? Well, it happens at the equilibrium position, the stable equilibrium position. At x0, U is minimum. So that means E minus U is maximum. There's a largest gap here. And so the velocity at the equilibrium position is largest. Okay. So when the object swings back, it passes through the equilibrium position at the highest velocity. And goes to the other side, it becomes a momentary rest again. It rolls back again. When it passes the equilibrium position, it gets the highest velocity again. So it goes swing back and forth like this. Is that clear? So anytime when you found in any position, if you want to find a V, you just minus E minus U multiplied by 2 over m, take a square root. Okay, that's just conservation of energy. Now, but we say that mechanical energy is conserved because we assume that internal force is a conservative force. So it only allows kinetic energy and potential energy to exchange each other. So but the total energy remain conserved. That relies on the assumption that there is no energy dissipation. All the internal force, they are the conservative force, but not the dissipative force. Okay, the dissipative force including friction, viscosity, etc. And there's no energy exchange with the surrounding. There's no external force pushing it. Okay, and those are the two conditions for the mechanical energy to conserve. If I have a frictional force that changes the energy into heat, and if I have an external hand pushing the whole thing, then the mechanical energy of the system itself will not be conserved. Okay. Now we consider a case of a friction because frictional force always cause a dissipation of energy in the system. So we would imagine if we apply the work energy theorem again, the frictional force will does a negative work because the frictional force is always in opposite direction to the displacement. So it does a negative work. And doing negative work on the system means the mechanical energy of the system will decrease. So that means the frictional force dissipates the energy of the system. Okay, and so the energy will lose. But we know that from the principle of conservation of energy, the energy will not disappear. It will only change to other form. So that other forms include internal energy, light and sound. Okay. If frictional force dissipate the energy, if the collision dissipate the energy may go to internal energy of the system, and in some special case, it may go to light or sound. Okay. But the energy has changed to another form only. It does not disappear. It does not annihilate. Okay. It always there. It just goes to another form. So the total energy on the universe is conserved, and that is known as a principle of conservation of energy. Okay. Now let us handle a problem with dissipation. Okay. Suppose we have an inclined plane, but you see I draw it like this, meaning that the inclined plane is rather rough. So there is a friction between the inclined plane and the block. Okay. Now I allow the block not allow the block to slide down, but I now initially my block is at the lowest position of the plane, and I push the block upwards with an initial velocity u. So I give the block a kick. I push it up with initial velocity u. I want to find the maximum height that the block can reach along the inclined plane. Okay, that's my problem of interest. So now I have to include the friction. Okay, now you may know how to calculate it by using the Newton's law, but now I do not use the Newton's law. I use the what? I use the conservation of energy, the work energy theorem. I allow the frictional force to thus work, and the negative work done by the frictional force is exactly equal to the change in the energy, mechanical energy of the system. I use this principle. Okay. Now I know that on the block there is a downward force of gravity mg, and there's a normal reaction from the inclined plane, and there's also a frictional force directed downwards along the inclined plane because I push the ball upward, so the frictional force must be downward. Okay, and the frictional force is equal to mu r, where mu is the kinetic friction coefficient. R is of course a normal force pressing the two surfaces together. Okay. So by resolving the force component, I know that because my block does not have a motion perpendicular to the inclined plane, so R is equal to mg cosine theta. R and mg cosine theta, they balance each other. Okay. And the frictional force is given by mu r. Mu is the coefficient of friction, kinetic friction. Mu r, and that's mu mg cosine theta. The frictional force does work. When I consider the block move up the plane by a certain distance s, the frictional force does a work of minus fs. The minus sign is there because the frictional force does negative work. The displacement goes up, but the frictional force goes down. So they're opposite direction. So the frictional force does a negative work, given by negative small fs. Okay. And that should be equal to what? Equal to the change in mechanical energy. Initially, if I take the lowest position to be the reference level of the potential energy, I initially only have the kinetic energy half mu squared. That is the kick. I give it the initial velocity, and that is the initial kinetic energy. When I go to the highest position along the plane, the kinetic energy gone, right? And all the energy become the potential energy. And the potential energy is mg s sine theta. This is the heights. The heights, if the displacement is s along the inclined plane, the heights that the object has raised is s sine theta. Okay, so I have mg s sine theta as the final potential energy. So this is the final mechanical energy minus the initial mechanical energy. Okay, So the change in mechanical energy is on the right-hand side. And on the left-hand side, we have the work done by the friction. Okay, is it clear? The work done by the friction change the mechanical energy. So I have the final mechanical energy, which is the top at the top position of the block, minus the initial mechanical energy, which is a lower position. Okay. So I can now solve the whole problem because I know that mu is what? The F is what? F is mu mg cosine theta. So I put it here for F. Okay. So I just solved this equation. I just move all the terms with S to one side. Okay, I pick out the factor S. And so I got S equal to U squared over 2G sine theta plus mu cosine theta. Okay, so that is the maximum height the block can reach. Okay. Now, so far we have learned Newton's law in two different ways. We have learned Newton's law in two different ways. The first way is that we learn Newton's law in terms of F equal to ma. And that is the equation of motion. With a given acceleration as a function of x and v, you solve the equation of motion F equal to ma, and you find the motion. You find the velocity and position at different time, right? So you can plot a graph of vt graph, you call it graph of xt graph. You know the velocity and the position at any time. You solve the whole motion. That is our first approach. And our first approach is the first 3 chapter we studied in this course, right? But we now prefer not to solve the differential equation because the differential equation is sometimes very complicated, very difficult to solve. Not all the motion can be solved the equation of motion. Sometimes the equation of motion is quite difficult to solve. And sometimes we are not interested to know the velocity and the position at any time. We do not want those details. But we can use an alternative approach. The alternative approach is the energy conservation. The energy conservation is another approach, which allows you, even if you haven't solved the whole motion, you can somehow relate the velocity of the object at different position or to the different position of the object. So when you have a roller coaster, for example, the track is very complicated, right? You cannot solve the equation of motion. You do not know the velocity and the position at a certain time, right? But somehow when the roller coaster rolls to a certain position, you know the degrees in potential energy and you can calculate the velocity by using the conservation of energy. And so that is another approach to give you some information about the system. You haven't solved the whole problem, but it always allows you to obtain some information about the system. It allows you to predict the velocity, for example, at different positions along a complicated track. Okay, so that is the energy approach. But the physics is the same. The Newtonian equation of motion is just the same as the principle of conservation of energy. Because we derive the conservation of energy from the Newtonian equation of motion. So they must be equivalent to each other, right? But how do the two mathematical relation related to each other is a question of interest. We have two formulations that looks quite different, but exactly how are they related? Okay, that is the interesting question. Now, mathematically, the equation of motion looks like this. The second derivative of the displacement with respect to time is the acceleration. And in the case of a conservative force, the acceleration only depends on the position. It does not depend on velocity. Now, this is a second order differential equation, which means that the displacement have a second derivative in time. So that is a second order differential equation. You have two derivatives in time. How about the conservation of mechanical energy? For conservation of mechanical energy, you have half mv squared plus ux equal to the total energy E. U is the potential energy, and half mv squared. V is just the x dt, is that right? And we have solved this, the V before. The V can be solved from this equation. The V can be found as square root 2e minus u over m, right? You may have a plus sign or minus sign because, due to the direction, but that doesn't matter, okay? Now you can see when comparing this equation and this equation, you find that the form is quite similar. But for the Newtonian equation of motion, it involves the second derivative of the displacement, d squared x dt squared. While for the conservation of mechanical energy equation, you only involve the first derivative, dx dt, right? Now you can see if you go from here to here, effectively you do an integration. When you start from a second derivative and you eventually can obtain the first derivative, that means you integrate, you effectively have integrated the equation of motion. So you reduce the order of that equation from second order to first order. Well, when did we do the integration? We actually do the integration. We do the integration here. Do you remember this slide? We multiply both sides with v, and we move the dt to one side, and we integrate both sides, right? So we have integrated, although we do not integrate it explicitly in terms of t, but we have actually integrated. And after integrated, we obtain the energy equation. That is how the integration comes from. So the two formulas, they are just related to each other by an integration. But the integration must involve an integration constant, right? And that integration constant is exactly what allows you to insert the initial condition, to impose the initial condition. But now the initial condition does not appear as the initial position on the initial velocity. It appears as the total energy. The total energy is the initial condition you specify at the beginning. At the beginning of motion, you specify the total energy of the system. That is the initial, one of the initial conditions. So E is actually the integration constant, okay? Effectively, an integration constant of this motion. So you now understand how the two formulas are related to each other. They are just an integration, integral. The energy equation is just the integral of the equation of motion. Now, and then I would refer you more to the integration on work and energy by looking at this e-learning module. Work and energy, work and PE, and definition of work, potential energy. You can have more review of this in this e-learning module. And if you want to go to 3-dimension, you have to learn, instead of just a line integral of f dx, you have to learn something called line integral, which allows you to calculate work done along very complicated 3-dimensional path. So you have to learn the new mathematical tools on line integral. And in 3-dimension, when you take the derivative, you have to take a gradient, okay? And a curl of a vector field allows you to calculate, to test whether a force is conservative or not. And those are the extension which goes beyond this course. But if you are strong enough in mathematical skills and you want to learn new things, these are the extension that are recommended for you. Okay, so if you are smart and you want to learn more, you can go to this extension. Okay, and this is the work and energy also in higher dimension. So this module are from Professor Yang, and they are not meant to be a test in this course. But if you want to learn more, then that is the position. Now, finally, I prefer to finish this chapter at this lesson. In next lesson, we have start a new chapter. So we just cover one more slide, and that's on power. What is power? Power is the rate of work done. It is the rate of energy transfer. How fast the energy is being transferred. It's not the amount of energy that is transferred. The amount of energy that is transferred is work. The power is the rate at which this energy is transferred. How fast is this transferred? You can transfer a very small amount of energy, but at a very high rate. Okay. For example, in an explosion, explosion is actually not transferring a very large amount of energy, but sometimes there is a large explosive force because the explosion takes place in a very short time. So the energy gets released in a very short time interval. And the explosion typically lasts for 1,000 of a second. So that is a very short time. And in that very short time, a definite amount of energy is released, and so that results in a high power. And that causes a destructive power. Okay. Now, we start from Newton's second law to calculate power. Okay. We form a dot product. We use the vector form, and we form a dot product of the F and on the right-hand side dv dt with another velocity v. So the left-hand side become F dot v, and the right-hand side become v dot dv dt. Now, by the product rule of differentiation, v dot dv dt is just d dt v dot v. Now, you just consider this as v squared. It is not exactly square, but it's a dot product between the two vectors. But the product will still apply. When you differentiate v dot v, you still got 2v dot dv. Okay, so the product will still apply for this case. So when I put the derivative to be v dot v within the derivative, I got additional factor of 1/2. Okay, because when I do the differentiation, I get additional factor of 2, and that needs to be cancelled by the factor 1/2. But v dot v is v squared, and I identify this as the kinetic energy. So taking the derivative of the kinetic energy means I'm now calculating the rate of change of kinetic energy. If the left-hand side is equal to the rate of change of kinetic energy, that means the left-hand side is the rate of doing work, and that is power. So I identify the left-hand side F dot V as the power. Okay, the power is the rate of work done by the force. And the unit of power is watt, and watt is just joules per second. Okay, and so that instantaneous power delivered by force can be calculated as F dot V. That is the idea. Okay. And so we end this chapter already. So if you have any questions, you can raise it now.